Hello everybody. This video is going to be about solving some partial fraction problems that, well, frankly, if you use the traditional method might make you cry a little bit. And so I want to show an alternative approach that might be a little bit, I don't know, more palatable. All right. I mean, if this problem gets hard enough, it doesn't matter which method you use, you're going to be frustrated by just how much brute force you have to do. But it is kind of fun to see some alternative approaches. So we'll do a couple examples in this video. The first one, I mean, it's not going to look like it's going to be so bad at the beginning. I have some function, s minus 4 over, let's say, s plus 1 cubed times s minus 3 squared. And I'd like to do the partial fraction decomposition. So, well, let's see. We have two sets of repeated linear factors. So the first one, s plus 1 cubed, we're going to need some constant over s plus 1 cubed, and then a constant over s plus 1 squared, and then a constant over s plus 1. And then we have the s minus 3 squared portion, so I'll need a constant over s minus 3 squared, and another constant over s minus 3. Okay, well, there's a lot going on here. And if we set it up in the traditional way, we would clear denominators, multiplying top by s plus 1 cubed times s minus 3 squared, which will yield s minus 4 equals, oh boy, here we go, a times s minus 3 squared plus b times s plus 1 times s minus 3 squared plus c times s plus 1 squared times s minus 3 plus d times s plus 1 cubed plus e times s plus 1 cubed times s minus 3. Woo! And here you start to see why we're not looking forward to going on with the traditional method on this problem. Now, we could use the cover-up method to get A and D quickly, right? Also, I call this the thumb method. It's also sometimes called the Heaviside method. So that won't be so bad, but maybe we are going to write this all out, right? So we're going to have to distribute all of this stuff. Oh boy, I don't want to, and you can't make me do it. You can't make me do it. I don't want to do it. So I want to try a different approach here. Okay, so what I'm going to do is, instead of distributing or multiplying through by the entire denominator, I'm only going to multiply through by, say, part of the denominator. Like, let's say we just multiplied through by s plus 1 cubed. So if instead I multiplied through by s plus 1 cubed, then I would have s minus 4 over, well, I don't get rid of this s minus 3 squared. Okay, and on the right-hand side, I'm going to have a plus b times s plus 1 plus c times s plus 1 squared. And then, you know what, let me just play a little game here. I'm just going to call this bit h of s. So if I call that h of s, then I'm going to have h of s times s plus 1 cubed. Okay, so h here is not a polynomial, so this is a rational function, but I don't really care what it is. Okay, so what this tells me is if I want to compute a, b, and c, all I need to do is expand this expression as a power series in s plus 1, and then find the coefficients of 1, s plus 1, and s plus 1 squared. And I can do that by just simply doing long division, well, maybe after a little bit of a rewriting here. All right, so this is where we have to do a little bit of work. So I want to rewrite this as in terms of s plus 1s. Now the numerator is going to be very, very easy. I can replace s minus 4 with s plus 1, and then I have to subtract 5. So s plus 1 minus 5 is s minus 4. All right, what about the denominator? Well, that's a little bit trickier. If I just make this s plus 1, I'm going to have to do some distributing and so forth. However, I made a video on something called the Ruffini-Horner algorithm, or Horner's method, and you might want to go check that out, because that video shows you how to take an expression like s minus 3 squared and rewrite it in terms of s plus 1. So we're going to use Horner's method. So this polynomial, the coefficient, there's just a 1 coefficient, and then there's no other term, so I use a 0 and a 0. And the root of this is 3, and I'm trying to write it in terms of s plus 1, which has root -1. So I need to go from 3 down to -1. So I'm going to basically be dividing by x plus 4, s plus 4, so I use a -4 here. There's 3 numbers, so I write 3 copies of 1. I draw some guidelines, and now -4 times 1 plus 0 is -4. -4 times 1 plus -4 is -8. And then -4 times -4 plus 0 is 16. And so this tells me I can rewrite my denominator as s plus 1 squared minus 8 times s plus 1 plus 16. And yeah, it's not so difficult to do this by hand, but you know what? If I made this into a cube or a fourth power, all of a sudden you're going to see, yeah, I want Horner's method. It's way too complicated doing this by hand. All right, so I have this new expression, and to make this look a little bit easier, let me make a simplification, just a little substitution. I'm just going to let u be s plus 1. So that this becomes u minus 5, or actually, in fact, I'm even going to write this in a different way. -5 plus u over 16 minus 8u plus u squared. And you'll see in a moment why I'm writing it in increasing order of power. So as I said, I want to compute a power series expansion and get the first 3 coefficients. So I can do that here using long division. So let's get to it. I'm dividing into -5 plus u, and I'm dividing 16 minus 8u plus u squared. So let's see. 16 goes into -5. Let's see, we need -5 over 16. So then I distribute, and I'll get -5 plus, let's see, this is going to be 40 over 16, which is 20 over 8, which is 10 over 4, which is 5 over 2. Okay, so 5 over 2u, and then minus 5 over 16u squared. I subtract. This is 0. U minus 5 halves u is going to be -3 halves u. And then we have plus 5 over 16 u squared. Okay, this is the first coefficient of my power series. All right, now I go to get the second coefficient. It's okay, what do I multiply 16 by to get -3 halves u? So I'm going to need a minus, and it looks like 3 over 32u. So when I multiply, right, 16 over 32 is a half, so we're going to get minus 3 over 2u plus, looks like, okay, 8 over 32 is a fourth, so this will be plus 3 over 4u squared, and then we'll have minus 3 over 32u cubed. Okay, and when I subtract, this is going to go away. 5/16 minus 3/4, so let's see, that's the same as 12/16. So we have -7/16 u squared. And then there's going to be more, but I don't really care because I'm only trying to get the first 3 terms of the power series expansion, and I can see immediately what that is going to have to be now. I need to ask, what is 16, how many times 16 go into -7/16 u squared? That's going to be minus 7 over 256 times u squared. Okay, and this will keep going. But I don't really care. I just want these 3 coefficients, because those 3 coefficients are precisely my A, B, and C. All right, everything else is going to be a higher power of u, and remember, u is s plus 1. So my A became -5 over 16. My B becomes -3 over 32, and my C becomes -7 over 256. And I can even put this now back into my original expansion. So somehow, right, sort of all at once, we're getting A, B, and C, which is pretty neat. Okay, well, if we want to get D and E to finish off the problem, we basically just play the same game now, right? I'll maybe call this G of S, so I don't have to worry about that bit anymore. And I'm going to, instead of multiplying through by S plus 1 cubed, I'll multiply through by S minus 3 squared. So when I do this again, so if instead I multiplied by S minus 3 squared, I'll end up with S minus 4 over S plus 1 cubed equals, well, now that first bit was G of S, and I multiplied that by S minus 3 squared, and I don't really care about it. It's really the other part I care about. So I had originally D over S minus 3 squared, but then I got rid of the S minus 3 squared, and then we have plus E times S minus 3. And so again, what we want to do is rewrite this in terms of S minus 3, and then find the power series expansion in terms of S minus 3. And all we need this time is actually the first two coefficients. So this should even be easier. Okay, again, the numerator is not bad, right? S minus 3 and then minus 1 will give me S minus 4. And in the denominator, let's see, I need, well, okay, I'm going to want to use Horner's method, right? So let's do this. The coefficient in front of S plus 1 cubed is 1, and then we have no S squared, or S plus 1 squareds, no S plus 1s, and no constant. All right, now I need to go from, okay, the root here is negative 1, and I want to write it in terms of the root of S minus 3, so that's 3. So to go from negative 1 to 3, I need to go up by 4. Okay, let's see. I have 4 here, so I'm going to write 4 copies of 1. Draw my guideline, and here we go. 4 times 1 plus 0 is 4. 4 times 1 plus 4 is 8. 4 times 1 plus 8 is 12. 4 times 4 is 16, plus 0, still 16. 4 times 8 is 32, plus 16 is 48. And then 4 times 16 plus 0 is 64. So this denominator becomes S minus 3 cubed plus 12 S minus 3 squared plus 48 S minus 3 plus 64. And again, I'll use a substitution to simplify this so it looks like negative 1 plus u over 64 plus 48u plus 12u squared plus u cubed. All right, here we go. The sort of the last step now. We need to do polynomial division. Negative 1 plus u, and we'll divide by 64 plus 48u plus 12u squared plus u cubed. All right, to get, let's see, what times 64 is negative 1? So negative 1 over 64. So that'll give me negative 1, and then we're going to have minus 48 over 64, which is, let's see, 8 goes in, or even 16 goes in, so 3/4 times, okay. And then what's going to be next? Well, actually, there's more coming, but I don't really care what it is because, well, let's see what happens, all right? So more is going to come. I'm going to subtract. These go away. U minus negative 3/4 u is 7 over 4u, and then there'll be more junk. But in the next step, I just ask, okay, what do I multiply 64 by to get 7/4 u? And that's going to be 7 over 256u. And of course, more junk will come, but I don't care about any of that. I only cared about the first two terms of the series expansion in terms of S minus 3. So I just need the negative 1/64 and the 7 over 256 for my D and E. So here we get minus 1 over 64 plus 7 over 256 times S minus 3. Okay, and we can put that back into our original partial fraction decomposition. So D now becomes, okay, we have minus 1/64, and e is 7 over 256. All right. Now, I'm not saying this was very fast. All right. Now, I will say I'm showing you more detail than you necessarily would have to write for yourself. All right. You can get rid of a lot of these intermediate explanation steps if you're kind of doing this privately. But you'll notice that we didn't have to do a lot of distribution here, right? We didn't have to go through and expand s plus 1 cubed and s plus 1 squared times s minus 3 and all that, and then solve a system of equations, right? Which, if you don't use the cover-up method, would be 5 equations maybe, right? Or 4 equations with 4 unknowns, right? There's 5 unknowns, in fact. There's a lot that's going to go on there, algebraically. Let me do another example. And so, by the way, this method is only meant to really apply when you have linear factors, when you have quadratic factors, assuming you're not going to break things up as a product with complex pieces. The quadratics just aren't going to allow this to work, but you can still use the method a little bit as long as you are willing to mix the methods a little. So let me show you. So let's do example 2. So example 2, we're going to have s squared plus 4s minus 9. And we're going to divide by, well, we'll use the same s plus 1 cubed, but now we'll have an irreducible quadratic. So we'll have s squared plus 2s plus 7. All right, so we know for partial fractions that this should split up as some constant over s plus 1 cubed plus a constant over s plus 1 squared plus a constant over s plus 1. And then because this is an irreducible quadratic, which we can check by looking at 2 squared minus 4 times 7, and we notice that's negative. So this over here, we're going to have s squared plus 2s plus 7, but we're not going to have a constant. We're rather going to have a linear function in the numerator, right? That's the payoff or the price you pay for having an irreducible quadratic. Okay, but I'm not going to worry about this right now. I'm just going to give this a name. How about we'll call it g of s for the garbage. Okay, so I'm going to play this same game where I'm just going to multiply through by the s plus 1 cubed. So when I do that, I have s squared plus 4s minus 9 over s squared plus 2s plus 7. And on the right-hand side, I'll have a plus bs plus 1 plus cs plus 1 squared plus, okay, now I have this g of s. Again, this is not a polynomial, and it's multiplied by s plus 1 cubed, but I don't really care. I'm not going to worry about it. The point is, I now basically am going to be trying to get some sort of a power series expansion in s plus 1, and I want the first 3 coefficients. Now, I'm going to want to write each of these polynomials in terms of s plus 1. But again, Horner's method is going to let us do that pretty quickly. So for this top one, the coefficients are 1, 4, and negative 9. And I want to write in terms of s plus 1, so this is going to be a negative 1. There's 3 terms, so I copy 3 ones. So negative 1 times 1 plus 4 is 3. Negative 1 times 1 plus 3 is 2. And then negative 1 times 3 plus negative 9 is negative 12. So the numerator is going to become s plus 1 squared plus twice s plus 1 minus 12. All right, now I need the denominator. So there the coefficients are 1, 2, and 7. And again, we're dividing here by negative 1. All right, I'm saying dividing because Horner's method is really extending synthetic division. So let's see here. We got 1, 1, 1. And let's see. Negative 1 times 1 plus 2 is 1. Negative 1 times 1 plus 1 is 0. And then negative 1 times 1 plus 7 is 6. So the denominator becomes s plus 1 squared, and then just plus 6. Oh, that's nice. Yeah, we probably would have seen that even faster if we just completed the square, right? Okay, but we didn't see it. We were just being blind. Cool. So now we play this game where we use a substitution just to make this look a little nicer. So we have negative 12 plus 2u plus u squared over 6 plus u squared. Okay, now we go to our long division. So for our long division, we have 6 plus, rather, negative 12 plus 2u plus u squared. And we want to divide by 6 plus u squared. All right, 6 goes into negative 12, negative 2 times. Let's see, we don't get any 2u's, but we will get negative 2u squared. We subtract, we're going to get 2u, and then plus 3u squared. Now, let's see, let's double check. What did we need? We needed, yes, the first 3 terms. So we were probably going to want to write things out nicely for a little bit anyway. So 6 goes into 2u. Well, let's see, I guess we're going to need a third times u times. So third times 6 is 2u. Third times u squared is going to be, so we don't get any of those, but we get 1/3 u cubed. So we subtract, and we have 3u squared minus 1/3 u cubed. Okay, and the third u cubed is not going to matter because, well, we're looking for the next term. 6 times what is 3u squared? That'll be a half u squared. Okay, and that's enough. So our coefficients are going to be negative 2, a third, and a half. So we head back up. There we go. We had negative 2, a third, and 1/2. Okay, so we can put that in to our original expansion, negative 2, a third, and a half. And you see, I'm putting more stuff down than you'd have to. Like, we didn't need to replace it over here. Right? We just write it down once. Okay, now, to get the d and the e, I'm just going to go back to the original method. All right, so I'm going to take this expression, I'll clear the entire denominator, and the beauty is I now have 3 of the 5 terms already, and finding the d and e then is going to be reasonably simple. So let's just jump down and do that down below. There we go. So when I clear denominators, it's going to look like s squared plus 4s minus 9 is equal to negative 2 times s squared plus 2s plus 7 plus a third times s plus 1 times s squared plus 2s plus 7 plus a half times s plus 1 squared times s squared plus 2s plus 7. And then this last bit is the ds plus e times s plus 1 cubed. Okay, so what I'm going to do to get my d is I'm going to look at the highest powered terms of s. These will be the 4th powers. And then my e's, I'm going to look at the constants. So for the s to the 4th powers, on the left I have none of them. On the right-hand side, we'll see, that's just a square. Here I get a cube. And here I can get an s squared times an s squared times a half. So I get a half s to the 4th. And then here I get ds times s cubed, so plus a d. And so my d is negative a half. That was really not that bad. Okay, now I'll look at the constants. So I have my constants here. On the left-hand side, I have negative 9. On the right-hand side, let's see, I have negative 2 times 7. It's negative 14. I have a third times 1 times 7. That's 7/3. I have a half times 1 times 7. That's 7/2. And then I have e times 1, so plus an e. All right, well, let's see. I'll put 14 on the other side. It'll give me 5, and then subtract these. So e is going to be 5 minus 7/3 plus 7/2. Let's see. That's going to be 21 plus 14 is 35/6. And so 5 minus 35/6 is negative 5/6. All right, so that wasn't so bad. I get my d and my e, negative a half and negative 5/6. So negative a half s minus 5/6. and I have found my partial fraction decomposition. So using this alternative approach, right, allows us to get at least the repeated linear factor stuff. And then once we've done that, yeah, we have to go back to the original method, but it wasn't really all that bad. We only had 2 unknowns left, and it was pretty easy to attack them, which is that should be a general phenomenon here. All right. Well, I hope this is enlightening and gives you some food for thought about other ways one could approach the partial fractions method. And also, hey, great advertisement for this Ruffini-Horner or algorithm or Horner's method. All right, have a wonderful day.